Hello, everyone. Today's presentation is about training vision models on geodata for the protection of water reservoir ecosystems. My name is Paulina. I am a senior data scientist at DeepSense AI, and I will present the presentation together with Zuzanna.
Hi everyone. I'm Zuzanna, and I work at DeepSense AI as a senior software engineer in machine learning. So during today's presentation, we'd like to share with you our recent experience of working with WWF on a project, and this project's goal was classification of small water bodies, for example, water reservoirs. And from the technical point of view, the highlight of this project was probably input data, which was geodata. So it included both visual features as well as geographic information. So why is it even important? Why is this task even of interest? Well, from the environmental point of view, a subtype of water bodies is actually interesting. In particular, oxbow lakes. You can see an example of an oxbow lake in the image on the left side of the image. Oxbow lakes are often host to unique ecosystems, and the flora and fauna that is often present there is very valuable in terms of studying and understanding and monitoring and also protection. However, the tricky part here is that oxbow lakes, by their nature, they change with time as the river ages, changes its course slightly. So oxbow lakes also may change their shapes, their locations, they may evolve or diminish. So it's really important to be able to distinguish oxbow lakes from other types of natural or artificial water bodies, such as ponds or reservoirs, etc. Okay, so our today's presentation will be divided into three main subjects. First, we'll tell you a bit more about the data that we used in our project. Then we'll share with you the solutions that we implemented and tried and tested. And finally, we'll also describe the results that we were able to achieve in the project so far. So as for the data, we worked with geodata, and geodata is basically just a name that we usually assign to rasters. Rasters consist of a visual layer and of map coordinates and projection. So the visual layer is basically just an image, and it could be different kinds of images. It can be an RGB image, it can be a vector graphic like a map. It can also be multispectral, as is usually the case in cases of satellite imagery. It can also just be a binary mask, as was the case in our study. And you can see a sample of this kind of binary raster on the right side of the screen. So rasters are usually stored in formats such as shapefiles or geotiffs. And if you're working with geodata manipulation, definitely the go-to library is GDAL. It's quite a light library, and it gives you a lot of options to process rasters, to understand them, to modify them. It also it's well established and has quite a large community. So if you ask a question on Stack Exchange, you'd probably be answered by some GDAL experts in a couple of days tops. But it has a learning curve, as is usually the case with large libraries. So if you're looking for a simpler task, and our task was kind of simpler in this aspect, you should probably try lightweight libraries such as GeoPandas, for example, which is quite nice. It can just install from PyPy, and it reads rasters into a form similar to Pandas data frames. Or Xarray, which is also very, very tiny, and it's quite useful for geometric comparison, quick operations like that. So the interesting thing about geodata is that thanks to the projection information, the location, you can always overlay additional data sources. And there are quite some open source resources out there, and also not open source, but somehow available in other ways. For example, from the open source resources, we can definitely recommend OpenStreetMap, which is basically a vector map that covers more or less the whole globe. And it's really useful if you want to understand your rasters better, if you want to understand the objects that you're looking at better, you should definitely try and just use OpenStreetMap to overlay your rasters on. And you can see if the object you're looking at is close to a city, close to a lake, or whatever. It's kind of useful that way. Also, another thing that might be of interest to some of you is that most European governments actually make available aerial imagery of their countries. And this kind of imagery is usually taken like once a year or once a couple of years. Usually it's quite tricky to actually download it, and not many people know about it. You have to get through a pretty horrible interface usually. But usually it's worth it if you just are interested to monitor your favorite town or your favorite place, basically in Poland, just how it changed over time. So it's definitely something to try as well. Okay, so as for our particular dataset, our dataset consisted of 3,981 binary raster images. And each of those binary rasters contained only one single water body, so one sample that we were supposed to classify. Of those 3,981 binary rasters, we had 1,380 oxbow lakes and a similar amount of artificial reservoirs and a similar amount of other natural water bodies. So these oxbow lakes could also be divided into three categories based on the ways they were actually connected with other water bodies or other water courses. On the right, you can see an actual sample from our dataset, binary raster, that is actually overlaid on the OpenStreetMap view that I described to you on the previous slide. Okay, so here you can also see samples from our actual dataset, and you can see that it's important to really have this projection information, because then you can refer to the actual scale, and you can see that the differences in scale can be very significant. So it's also important to include them somehow. As for our data, apart from the binary rasters of our samples, we also had available a raster with all water courses. So this image on the right is actually, it's not a fancy graphic from Wikipedia. It's just an actual raster visualized in QGIS, which is quite a nice visual interface for visualizing rasters that we can also recommend. And these water courses are basically all water channels, rivers, etc. in Poland. And it was particularly important as during our project, we learned that the experts from WWF, when they actually make the decision whether this water body is an oxbow lake or not, they heavily take into account the neighboring water courses, such as rivers, their shapes, their widths, etc., etc. So it was quite important that we also include that information for our models somehow. However, the other sources that I explained before, like satellites, aerial imagery, or map layers, were not available for us during this phase of the project. Okay, that's pretty much it from the data perspective. Now Paulina will take over to tell you a bit more about our solutions.
Okay, thank you, Zuzanna. So now let me tell you a little about our pipeline and the models that we used. So with raster image as an input, it seems for us that we have two natural paths for pipeline. So the first approach is to just end-to-end visual classification model. This is the top track in the diagram on the slide. So here the raster image goes to the model and is immediately classified into one of the classes. So various types of the convolutional neural networks model works here, such as ResNet, VGG, or Inception. The second approach is shown below and has two stages. First, we use an encoder to create embedding from the raster image. Then we use the traditional classifier to determine the class of the object. So here, as traditional classifier, I mean the models that usually operate on tabular data, such as k-nearest neighbor or random forest. However, apart from the raster images, we also have watercourses data. So the question is, where can this information be used and how? Well, we can incorporate watercourses data at every step if you want to. And we tried 3 ways of including this information. And how we did it turns out to be crucial for us. So now I will tell you briefly about each of them. The first way is to use the raster image and watercourse data directly in the classification model. So here we asked ourselves what information from the watercourses should be used. It makes no sense to use data from all over the Poland. So here we refer to specialists, and it turns out that when determining the water body class, the neighboring watercourses are the most important. So what we did was we used the watercourses within the defined radius from our body of water and prepare a raster from it. To prepare this as an input for our model, we need to incorporate this together into a single tensor. It can be treated as single channel, for example, with different intensity, or as 2 independent channels. We focused on experiments with 1 channel. A classification model that we used include VGG, ResNet, MobileNet, GoogleNet, and so on. We used both pre-trained models and training from scratch. The difference between the results here was insignificant. The second approach is similar, but here we create embeddings in the first step, and then we do the classification. So we use the watercourses data as before, and in a new way, we also create embeddings vectors separately for the raster image and the neighboring watercourses, and then we combine them. Such approaches were easy to test, but unfortunately did not produce the expected results. As encoders, we used similar models as before. And for the traditional classification models, we tried to use logistic regression, k-nearest neighbor, support vector machines, random forest, and XGBoost. And we go to the third approach. So here only the input raster image is used to create embedding, while the watercourses data is used to create features. So, and then embedding combined with features is used by the classification model. The main advantages of this approach is that we can include this information about watercourses outside our margin, and we don't have to worry about scaling. And here, feature engineering was the most important thing. So we added a lot of information regarding location, size, distance from the nearest watercourses, and so on. And now I'll move on to the most interesting part, which is the results. Here is a summary of our best solution. So it turned out that the third approach was the most successful. So the best encoder was ResNet 18, best classifier, XGBoost. Additional features that we used, it was location, at the size of the input raster. We used first and second moments of area. It was our attempt to represent the shape of the object. Moment of area is a geometrical property which reflects how points are distributed with regard to an axis. And of course, we use information about nearby water courses that may have an impact of the water body class, like distances or size. The exact numbers that we obtained on the test dataset are presented in the table at the bottom of the slide. So as you can see, we managed to achieve very high results. I have also prepared a confusion matrix so that your classes are shown as rows and our predictions are as columns. We have few mistakes, as you can see, mostly between artificial reservoirs and oxbow lakes, but it looks pretty good. However, this is not the end of our ideas. We tried the most obvious approaches to us, but there is room for improvement. You can see some of our ideas here. First of all, we could use additional data sources, such as map information. For end-to-end approach, we focused on experiments with one channel. We could try an approach with separate channel for water courses. And it would be worth checking other, more interesting model architectures. For the two-step approach, we should try assembling, for sure, and more feature engineering. For example, we could try estimate the width of the water courses. So there are still many untested approaches and ideas, and we hope to improve our results even more. Yes, and I will end the presentation here. Thank you for your attention.
Thank you.
Thank you, Paulina and Zuzanna. Let's have a virtual round of applause for our speakers. It was a very enlightening presentation, and we have some questions from the audience. So let me maybe get to the questions. And the first question is, would you recommend any sources for satellite imagery of Poland, ideally divided into free and paid sources?
Okay, so I can answer that. And of course, it would be probably easier for me to provide you with like an offline list of links if you'd like. But just for a short answer here. So first of all, often when we're talking about, overhead imagery, people assume that it's satellite, but you have to keep in mind that there's a lot of aerial imagery, which is much cheaper actually to obtain. And it's in effect way more available, and it's often it has often better resolution and it's easier to process in most cases. So please keep in mind that aerial imagery is also something you should definitely check out. As for satellite imagery is more expensive, so it's usually commercial. There are many private providers that you can totally check out, but as for the government source, you can go to the Polish site, which is called polsa.gov.pl, and there you have options to somehow read about the data they're gathering, and maybe if you reach out to them, you can actually get them for free, but that's definitely more of a problem. As for there's also this Polish website like satelita.mapa.info.pl, which I'm not sure about the usability of their API, but it's also something you could check out. But for aerial imagery, you have more resources. You also have two useful governmental Polish websites. One is called pzgik.geoportal.gov.pl, and another is called gugik.gov.pl. And you can, from the first site, you can actually get some of aerial imagery over Poland for free. So definitely check that out.
Yeah, thanks, Zuzanna, for an extensive answer. We have some more questions here from the audience. Let me ask you the second question with the most, like the biggest number of votes. It is, you mentioned some libraries for geodata and the learning curve. How do you think? Is it difficult format to work with someone who has never had experience with it? Are there a large number of tutorials and things that work out of the box, or is this format like problematic even to start with?
Okay, I will start. It was my first time to work with geodata, and yes, it was difficult. It was hard, but there are some good tutorials. I recommend starting with GeoPandas library and tutorials there, I think. But Zuzanna has more experience, so.
Yeah, I kind of started with, the hard way with Jido when I first started with it. But something that got me started like pretty quickly were the SpaceNet challenges. I don't know if you're familiar with that, but these are like, there's a set of challenges, machine learning challenges, deep learning challenges, where you can take part and actually win some money. It's about processing mostly satellite imagery. And there's quite a large community. There are leaderboards as in Kaggle, and there's there are many resources there, and you can also like ask questions in the forums dedicated to SpaceNet. So yeah, I'd do that if you want to just start with this format in general.
Okay, let's ask one more question. So one of the participants is asking, how will the model be used in production? Who is its target user? Did you also create any application?
Okay, so we created application, but the application is mainly for educational purpose. And and the second part of the question.
Oh, yeah. Did you create? Yeah, the question was how it will be used in production. Who will be user and who will be the user of, or did you create some application? Yeah, so it was basically like
Okay,
that.
so the end user, there is no end user. The main point of our project was to find all expos in Poland, and then create a report and show it to I don't government. I don't know, someone who is important somewhere. Yeah, it wasn't our part. I'm not sure, but I can check if you're interested.
Okay, well, thanks a lot for the answer and for the presentation. It was really enjoying to watch. And yeah, I think we should probably start slowly moving towards next presentation.